A charge-coupled device is a device for the movement of electrical charge, usually from within the device to an area where the charge can be manipulated, for example conversion into a digital value. This is achieved by shifting the signals between stages within the device one at a time. CCDs move charge between capacitive bins in the device, with the shift allowing for the transfer of charge between bins. The CCD is a major piece of technology in digital imaging. In a CCD image sensor, pixels are represented by p-doped MOS capacitors. These capacitors are biased above the threshold for inversion when image acquisition begins, allowing the conversion of incoming photons into electron charges at the semiconductor oxide interface. The CCD is then used to read out these charges. Although CCDs are not the only technology to allow for light detection, CCD image sensors are widely used in professional, medical, and scientific applications where high-quality image data is required. In applications with less exacting quality demands, such as consumer and professional digital cameras, active pixel sensors are generally used. The large quality advantage CCDs enjoyed early on has narrowed over time. History. The charge-coupled device was invented in 1969 at AT&T Bell Labs by Willard Boyle and George E. Smith. The lab was working on semiconductor bubble memory when Boyle and Smith conceived of the design of what they termed, in their notebook, charge bubble devices. The device could be used as a shift register. The essence of the design was the ability to transfer charge along the surface of a semiconductor from one storage capacitor to the next. The concept was similar in principle to the bucket brigade device, which was developed at Philips Research Labs during the late 1960s. The first patent on the application of CCDs to imaging was assigned to Michael Thompson. The initial paper describing the concept listed possible uses as a memory, a delay line, and an imaging device. The first experimental device demonstrating the principle was a row of closely spaced metal squares on an oxidized silicon surface electrically accessed by wire bonds. The first working CCD made with integrated circuit technology was a simple 8-bit shift register. This device had input and output circuits and was used to demonstrate its use as a shift register and as a crude 8-pixel linear imaging device. Development of the device progressed at a rapid rate. By 1971, Bell researchers led by Michael Thompson were able to capture images with simple linear devices. Several companies, including Fairchild Semiconductor, RCA and Texas Instruments, picked up on the invention and began development programs. Fairchild's effort, led by ex-Bell researcher Gil Amelio, was the first with commercial devices, and by 1974 had a linear 500-element device and a 2D 100 by 100 pixel device. Stephen Sasson, an electrical engineer working for Kodak, invented the first digital still camera using a Fairchild 100 by 100 CCD in 1975. The first KH-11 Canon reconnaissance satellite equipped with charge-coupled device array technology for imaging was launched in December 1976. Under the leadership of Kazuo Iwama, Sony also started a large development effort on CCDs involving a significant investment. Eventually, Sony managed to mass-produce CCDs for their camcorders. Before this happened, Iwama died in August 1982. Subsequently, a CCD chip was placed on his tombstone to acknowledge his contribution. In January 2006, Boyle and Smith were awarded the National Academy of Engineering Charles Stark Draper Prize, and in 2009 they were awarded the Nobel Prize for Physics, for their invention of the CCD concept. Michael Thompson was awarded the 2010 National Medal of Technology and Innovation for pioneering work in electronic technologies including the design and development of the first charge-coupled device images. He was also awarded the 2012 IEEE Edison Medal for pioneering contributions to imaging devices including CCD images, cameras and thermal images. Basics of operation. In a CCD for capturing images, there is a photoactive region, and a transmission region made out of a shift register. An image is projected through a lens onto the capacitor array, causing each capacitor to accumulate an electric charge proportional to the light intensity at that location. A one-dimensional array, used in line-scan cameras, captures a single slice of the image, whereas a two-dimensional array, used in video and still cameras, captures a two-dimensional picture corresponding to the scene projected onto the focal plane of the sensor. Once the array has been exposed to the image, a control circuit causes each capacitor to transfer its contents to its neighbor. The last capacitor in the array dumps its charge into a charge amplifier, which converts the charge into a voltage. By repeating this process, the controlling circuit converts the entire contents of the array and the semiconductor to a sequence of voltages. In a digital device, these voltages are then sampled, digitized, and usually stored in memory. In an analog device, they are processed into a continuous analog signal, which is then processed and fed out to other circuits for transmission, recording, or other processing. Detailed physics of operation. Charge generation. Before the MOS capacitors are exposed to light, they are biased into the depletion region. In N-channel CCDs, the silicon under the bias gate is slightly p-doped or intrinsic. The gate is then biased at a positive potential, above the threshold for strong inversion, which will eventually result in the creation of a N-channel below the gate as in a MOSFET. However, it takes time to reach this thermal equilibrium, up to hours in high-end scientific cameras cooled at low temperature. Initially after biasing, the holes are pushed far into the substrate, and no mobile electrons are at or near the surface. The CCD thus operates in a non-equilibrium state called deep depletion. Then, when electron-hole pairs are generated in the depletion region, they are separated by the electric field. The electrons move toward the surface, and the holes move toward the substrate. 4 pair generation processes can be identified. Photogeneration, generation in the depletion region, generation at the surface, and generation in the neutral bulk. The last 3 processes are known as dark current generation, and add noise to the image. They can limit the total usable integration time. The accumulation of electrons at or near the surface can proceed either until image integration is over and charge begins to be transferred, or thermal equilibrium is reached. In this case, the well is said to be full. The maximum capacity of each well is known as the well depth, typically about 105 electrons per pixel. Design and manufacturing. The photoactive region of a CCD is, generally, an epitaxial layer of silicon. It is lightly p-doped and is grown upon a substrate material, often P++. In buried channel devices, the type of design utilized in most modern CCDs, certain areas of the surface of the silicon are ion implanted with phosphorus, giving them an N-doped designation. This region defines the channel in which the photogenerated charge packets will travel. Simon S.Z.E. details the advantages of a buried channel device. This thin layer is fully depleted and the accumulated photogenerated charge is kept away from the surface. This structure has the advantages of higher transfer efficiency and lower dark current, from reduced surface recombination. The penalty is smaller charge capacity, by a factor of 2 to 3 compared to the surface channel CCD. The gate oxide, i.e., the capacitor dielectric, is grown on top of the epitaxial layer and substrate. Later in the process, polysilicon gates are deposited by chemical vapor deposition, patterned with photolithography, and etched in such a way that the separately phased gates lie perpendicular to the channels. The channels are further defined by utilization of the Locos process to produce the channel stop region. Channel stops are thermally grown oxides that serve to isolate the charge packets in one column from those in another. These channel stops are produced before the polysilicon gates are, as the Locos process utilizes a high-temperature step that would destroy the gate material. The channel stops are parallel to, and exclusive of, the channel, or charge-carrying, regions. Channel stops often have a P+ doped region underlying them, providing a further barrier to the electrons in the charge packets. The clocking of the gates, alternately high and low, will forward and reverse bias the diode that is provided by the buried channel in the epitaxial layer. This will cause the CCD to deplete near the PN junction and will collect and move the charge packets beneath the gates, and within the channels, of the device. CCD manufacturing and operation can be optimized for different uses. The above process describes a frame transfer CCD. While CCDs may be manufactured on a heavily doped P++ wafer, it is also possible to manufacture a device inside P wells that have been placed on an N wafer. This second method, reportedly, reduces smear, dark current, and infrared and red response. This method of manufacture is used in the construction of interline transfer devices. Another version of CCD is called a peristaltic CCD. In a peristaltic charge-coupled device, the charge packet transfer operation is analogous to the peristaltic contraction and dilation of the digestive system. The peristaltic CCD has an additional implant that keeps the charge away from the silicon dioxide interface and generates a large lateral electric field from one gate to the next. This provides an additional driving force to aid in transfer of the charge packets. Architecture. The CCD image sensors can be implemented in several different architectures. The most common are full-frame, frame transfer, and interline. The distinguishing characteristic of each of these architectures is their approach to the problem of shuttering. In a full-frame device, all of the image area is active, and there is no electronic shutter. A mechanical shutter must be added to this type of sensor or the image smears as the device is clocked or read out. With a frame transfer CCD, half of the silicon area is covered by an opaque mask. The image can be quickly transferred from the image area to the opaque area or storage region with acceptable smear of a few %. That image can then be read out slowly from the storage region while a new image is integrating or exposing in the active area. Frame transfer devices typically do not require a mechanical shutter and were common architecture for early solid-state broadcast cameras. The downside to the frame transfer architecture is that it requires twice the silicon real estate of an equivalent full-frame device, hence, it costs roughly twice as much. The interline architecture extends this concept one step further and masks every other column of the image sensor for storage. In this device, only one pixel shift has to occur to transfer from image area to storage area, thus, shutter times can be less than a microsecond and smear is essentially eliminated. The advantage is not free, however, as the imaging area is now covered by opaque strips, dropping the fill factor to approximately 50% and the effective quantum efficiency by an equivalent amount. Modern designs have addressed this deleterious characteristic by adding microlenses on the surface of the device to direct light away from the opaque regions and on the active area. Microlenses can bring the fill factor back up to 90% or more depending on pixel size and the overall system's optical design. The choice of architecture comes down to one of utility. If the application cannot tolerate an expensive, failure-prone, power-intensive mechanical shutter, an interline device is the right choice. Consumer snapshot cameras have used interline devices. On the other hand, for those applications that require the best possible light collection and issues of money, power and time are less important, the full-frame device is the right choice. Astronomers tend to prefer full-frame devices. The frame transfer falls in between and was a common choice before the fill factor issue of interline devices was addressed. Today, frame transfer is usually chosen when an interline architecture is not available, such as in a back-illuminated device. CCDs containing grids of pixels are used in digital cameras, optical scanners, and video cameras as light-sensing devices. They commonly respond to 70% of the incident light, making them far more efficient than photographic film, which captures only about 2% of the incident light. Most common types of CCDs are sensitive to near-infrared light, which allows infrared photography, night vision devices, and zero-lux video recording, photography. For normal silicon-based detectors, the sensitivity is limited to 1.1 micrometers. One other consequence of their sensitivity to infrared is that infrared from remote controls often appears on CCD-based digital cameras or camcorders. If they do not have infrared blockers, cooling reduces the array's dark current, improving the sensitivity of the CCD to low light intensities, even for ultraviolet and visible wavelengths. Professional observatories often cool their detectors with liquid nitrogen to reduce the dark current, and therefore the thermal noise, to negligible levels. Use in astronomy. Due to the high quantum efficiencies of CCDs, linearity of their outputs, ease of use compared to photographic plates, and a variety of other reasons, CCDs were very rapidly adopted by astronomers for nearly all UV to infrared applications. Thermal noise and cosmic rays may alter the pixels in the CCD array. To counter such effects, astronomers take several exposures with the CCD shutter closed and opened. The average of images taken with the shutter closed is necessary to lower the random noise. Once developed, the dark frame average image is then subtracted from the open shutter image to remove the dark current and other systematic defects in the CCD. The Hubble Space Telescope, in particular, has a highly developed series of steps to convert the raw CCD data to useful images. CCD cameras used in astrophotography often require sturdy mounts to cope with vibrations from wind and other sources, along with the tremendous weight of most imaging platforms. To take long exposures of galaxies and nebulae, many astronomers use a technique known as auto-guiding. Most auto-guiders use a second CCD chip to monitor deviations during imaging. This chip can rapidly detect errors in tracking and command the mount motors to correct for them. An interesting unusual astronomical application of CCDs, called drift scanning, uses a CCD to make a fixed telescope behave like a tracking telescope and follow the motion of the sky. The charges in the CCD transferred and read in a direction parallel to the motion of the sky, and at the same speed. In this way, the telescope can image a larger region of the sky than its normal field of view. The Sloan Digital Sky Survey is the most famous example of this, using the technique to produce the largest uniform survey of the sky yet accomplished. In addition to astronomy, CCDs are also used in astronomical analytical instrumentation such as spectrometers, color cameras. Digital color cameras generally use a biomask over the CCD. Each square of 4 pixels has one filtered red, one blue, and 2 green. The result of this is that luminance information is collected at every pixel, but the color resolution is lower than the luminance resolution. Better color separation can be reached by 3 CCD devices and a dichroic beam splitter prism that splits the image into red, green and blue components. Each of the 3 CCDs is arranged to respond to a particular color. Many professional video camcorders, and some semi-professional camcorders, use this technique. Although developments in competing CMOS technology have made CMOS sensors, both with beam splitters and biofilters, increasingly popular in high-end video and digital cinema cameras. Another advantage of 3CCD over a biomask device is higher quantum efficiency. This is because in a 3CCD device most of the light entering the aperture is captured by a sensor. While a biomask absorbs a high proportion of the light falling on each CCD pixel. For still scenes, for instance in microscopy, the resolution of a biomask device can be enhanced by microscanning technology. During the process of color co-site sampling, several frames of the scene are produced. Between acquisitions, the sensor is moved in pixel dimensions, so that each point in the visual field is acquired consecutively by elements of the mask that are sensitive to the red, green and blue components of its color. Eventually every pixel in the image has been scanned at least once in each color and the resolution of the three channels become equivalent. Sensor sizes. Sensors come in various sizes, or image sensor formats. These sizes are often referred to with an inch fraction designation such as 1, 1.8, or 2/3, called the optical format. This measurement actually originates back in the 1950s and the time of Vidicon tubes.